by, and I wanted to talk.
All right, our last lesson, we were looking at doing one-dimensional collisions. So those were a little bit easier to solve mathematically because we're only dealing in one direction. So we either had an object moving and it hits another object head-on, so we have two head-on collisions, or we could have one going one way and it hits another one going the other way, like a rear end or collision from behind. Or we also looked at ones that were moving and hitting a stationary object. And then whether the objects bounce apart, stick together, whatever, we did lots of different examples. Basically, they're all the same thing using the basic formula. Remember, we did mass of one times the velocity, mass and velocity of the other, equals our mass and velocity after of each. Okay, so that was basically our formula we were using. So what's changing now is we're going to be still doing the same thing, but instead of just basically plugging the numbers in the formula and solving it, we have to worry about vectors because we're dealing with two dimensions. So what's going to be happening now is we're going to have one object going at an angle, and it's going to collide with some other object at an angle, and then the two results are going to bounce apart or stick together or whatever. So as soon as we get two dimensions, things get quite a bit more complicated. We've got to be really careful with our diagrams, be careful drawing the vectors and doing our calculations. So before we start looking at an example, let's do just kind of making sure we get clear of some of the terminology and how we want to draw these diagrams. So the first one, it says we got two moving pool balls, so they have the same masses, and they're going to glance together. So glancing means sort of like a side swipe or just sort of a bouncing collision. So it says they strike each other with an angle of 30 degrees between them. So that means we'd have one ball, suppose it's going down at an angle like that, and our other ball could be going upwards, it could be going horizontal, doesn't really matter, but the idea is we got 30 degrees between the two. Okay. Typically, if that's the case, and if they were going at similar speeds, similar masses, then our resultant would be likely they would bounce apart. So that top one would bounce and kind of go the one angle, and maybe the bottom one would do the same. Okay, so I guess I should have color-coded them. So let's erase that. We'll start over here. So let's suppose our red one goes down at an angle, and let's draw the separate one as blue. So it's going to go up, and we got 30 degrees between the two. Then after they collide, so we'll have some sort of collision there. And then this one will go back down, and the red one would likely bounce back up, something like that. Okay. Does it mean that they're going to bounce back again at 30 degrees? Not necessarily. If they were the exact same speed, the exact same mass, yeah, then they would bounce back at 30 degrees. But if all of a sudden one is way faster or way more massive, it'll have larger momentum, which would then sort of dominate the collision. So we don't necessarily know what the angle is it'll be until we do the calculations. Okay, so let's draw one more. So it says we got a ball that's going to strike a stationary one, and then they move off with an angle of 60 degrees between them. So in this case, let's suppose we got one ball coming in. It's going to hit one that's stationary, and then after the collisions, we'd have our collision, and then we'd have the red one going off in one direction, the blue one going off maybe in a different direction, and it's saying we got 60 degrees after the collision. Okay, so you get the idea. That's sort of how we want to draw our diagrams. We don't necessarily have to draw the balls and the collisions and all that, but we really want to be careful with drawing our vectors properly. So let's do an example. So the key thing that we got to remember is our total momentum is what we're dealing with. We're only working with momentum again, just like we did with one dimension, but we have to make sure that our x and y components before and after equal, not just necessarily the total momentum because of the angles. So let's draw our first one here. It says we got a 1.2 kilogram red ball moving to the right at 17.1. So let's draw that. So we got 1.2 kilograms, 17.1 meters per second, and it says it's going to strike a stationary blue ball. So that one's not moving. Okay, and then, so that's our before. So now our after, it says the red ball is going to go 13.5 at 23 degrees above. So our red ball is going to go up something like that at 23 degrees above the horizontal and 13.5 meters per second. The question's asking what is the blue ball doing. So just using common sense, it's likely going to, if the red one's going to bounce up, probably our blue one is going to go down somewhere, but we don't know how fast or at what angle. So to solve these, what we got to work with is we have to deal with momentum only. We don't want to be working with speeds and masses and all that. So let's calculate the momentum of the original one. So P equals mv. So we'd have 1.2 times 17.1. So that gives us an answer of 20.52 kilograms meters per second. We don't need to worry too much about the units because we're dealing with momentum all the way through. So that's our only initial momentum. We have just a horizontal vector of 20.52. All right, so now the trick is, how do we connect that to the momentum afterwards? So what we want to do is we want to now change our, I'm going to erase these diagrams just so I can get colors. So this one was at what angle, and let's suppose our blue one is at down at some sort of angle, and that's it. So now we know our momentum of the red ball after, that was given to us. It was a speed of 13.5, and it's still 1.2 kilograms. So we can calculate its momentum. So let's go mass times velocity. So 13.5 times a mass of 1.2, and that'll give us an answer of 16.2. So let me erase our speed. Actually, what I'll do is I'll redraw it. Okay, so that red ball that was shooting up at an angle, so I'll draw that one. So it has a momentum of 16.2, and we know the angle is going to be 23 degrees. So now our next step is, let's figure out its components. So we can't deal with angles, we want to deal with horizontal and vertical components. So we'll have a horizontal component. I'll draw that in as red. And then we're also going to get a vertical component. I'll draw that one in as green. Okay, so we need to calculate those. So just use regular trig. So we'd have sine 23 is our y direction over 16.2. So we get an answer of roughly 6.3. And then we want to do the same thing for the x direction. So we want to go cos 23 equals x over 16.2. So cos 23 times 16.2 gives us an answer of 14.9. Okay, so in our diagram, let me just erase so I got a little more room here. So we have 6.3 going up, and then we'd have 14.9 horizontally. Okay, so let's go back to our original setup. And I'm going to go to a new page here that's blank. So let's go before again. We have 20.52. So I'm going to redraw that. So our vector to start was a momentum of 20.52. And then our after, we had 14.9 to the right. And we had 6.3 up. Okay, so that was our final red ball's vectors. And then the only other thing we had left was to calculate the blue ball. So we estimated the blue ball would go downwards at some sort of angle, and it doesn't really matter. You can use some common sense to estimate it, but we don't have to get it exact. The math will sort of take care of itself. So if we go back to this diagram, let me just kind of show you here. So we got a horizontal vector and a vertical vector for the one that we're looking for. So if we can calculate those components, we then should be able to figure out what our final answer should be. So off our diagrams, what we need to do then is we need to calculate the vertical and the horizontal components of that last vector, and then we should be good. Okay. So using conservation of momentum now, let's do our horizontal first. We got 20.52 was our initial. That has to equal our final. So we got 14.9 in the final direction, plus we'd have the one that we're looking for. So we just have to basically solve for x. So go 20.52 minus 14.9. And that gives us an answer of 5.62. And do the same thing for our vertical direction. Okay, what was our vertical motion to start with? 0. There wasn't any. So we have 0 to start with, and we have 6.3 up. So that means our y has to be negative 6.3. Otherwise, we wouldn't get it equal to 0. And that's it. So we've got our two components figured out. So let me kind of resketch this again. So we've got 6.3 going down. And we can write it as a negative you want. Sometimes it's a good idea so you don't forget. And we have 5.6. I'll just keep it rounded to one decimal. So 5.6 going to the right. So now we're good to go. We're ready to solve for our final answer. So we need to figure out our hypotenuse, and we want that angle. So if we just do Pythagorean theorem, that'll give us our hypotenuse. So that'll give us 8.4. And let's use tangent to figure out our angle. So our angle would be 6.3 opposite over adjacent. So go second tan, 6.3 divided by 5.6. And that gives us an angle of about 48 degrees. Okay, so what you just got to be careful now is that our final answer? If we go back to our question, the original question was determine the final velocity of the blue ball. So what we just figured out was the momentum, right? This was our momentum, so that's in kilograms, meters per second. So we've got our momentum and our angle. So the only thing we got left to do is figure out the velocity. So based on our formula, our velocity would be momentum divided by mass. So all we have to do is take that 8.4 divided by the mass of the blue ball, which was 2.31 in our original question. So we divide that out. So 8.6 divided by 2.31 gives us a final answer of 3.7. So then our final vector answer should be 3.7 meters per second as our speed, and we're doing it at 48 degrees south of east. And that would be our complete final answer. So you can see we're still doing the same thing. We're still using P equals MV. What's different though now is we're doing just the X direction components. They have to equal each other. And then just our Y direction components. And usually as long as we have one triangle, we can add and subtract to figure out whatever the remaining one is. Let's do one more example and then that'll be it. So this example, we've got a 1.2 kilogram red ball moving downwards. So we got 1.2 kilograms. It's moving at 10 meters per second. So if we go 1.2 times 10, that'll give us a momentum of 12. And then our blue one, it says it strikes a blue ball. That's 2.31. And it's moving at 15. So that gives us a momentum of 34.65. Okay. And let's go to the after effects. So the after, we have a So our after effects, we've got still the red ball, so it's still 1.2, but it says it's moving at 13.5 now. So that gives us a momentum of 16.2. And the question is, what is the velocity of the blue ball? So we're going to have to figure out that momentum of the blue one. Once we have the momentum, we should be able to figure out the velocity and the angle, just like we did on the last question. So with this question, then we're going to have to do sort of the same thing. So we're going to need to figure out the x components, the horizontal components of all of the different vectors. And then we're also going to have to figure out the vertical component. So the red one is going down and over. Let's do that in blue. Okay, so we got the one going down and to the right. The blue ball went up and to the right. Our red ball, the way the diagram is up and to the right, and our blue ball is downwards. So what we want to do then is calculate all of our vector components for all three triangles and then add and subtract them to combine them to get the new one. So on this page I've got a new diagram, so let's use that. So we've got our original. So the notes here, he's got the momentum of the red ball in the y direction, but we don't need to get that picky. We can just actually calculate it. So if we go sine 30 times 12, that'll give us 6. And if we go cos 30 times 12, that gives us 10.39. So let's round it off to 10.4. Do the same thing for the blue ball before and after. So we'd have cos 40 times 34.7. That gives us 26.6. And let's do our y direction, the same thing. So it'll be sine 40 times 34.7. And that gives us 22.3. Okay, so that's our initial before vector. So we got 6 down and 10.4 to the right. And then for our second ball, the blue ball is 22.3 up and 26.6 to the right. Why is the blue numbers quite a bit bigger? Well, remember it was a larger ball and it was going quite a bit faster. So we have more momentum on that blue ball. So it does make sense that our momentum after should be the same. Our momentum components should be larger as well. Okay, so now our after vectors, we got to do the same thing. We got 25 degrees, so let's do the y direction first. So we'll have sine 25 times 16.2. So that gives us 6.8. And cos 25 times 16.2 gives us 14.7. Okay, so we have all of our vectors. So in the previous page, let me just go back to the previous page. So we have all of our same numbers. We used 34.7 for this one instead of 34.65, but it's close enough. We don't need to get too picky with our rounding. So we have everything right, but when we look at our diagram, we assume that the blue one would go downwards and to the right. And you can draw it like that, it's totally fine, but what we're going to find out with this one is that actually it doesn't go in that direction after all once we do our components. So let's do our total before. So our total before, we've got 10.4 to the right and 26.6 to the right. So when we add these together, that's going to give us 36, 37. So that'll give us 37 to the right. And if we add our vertical components, we got 22.3 up. And we got 6 going down. So 22.3, this one, let's put it as a negative 6. So 22.3 plus negative 6 give us 16.3 up. So that's our two net results for our before. So that means our after has to be the same, right? We have to get the exact same answer. So once again, if we kind of think of it that way, we got our 10.4. Let me write it again here a little bit differently. So we have 10.4 plus 26.6. That's going to equal our 14.7 to the right plus are unknown. So let's call it x. So we'll get our 37 minus 14.7. And that gives us an answer of 22.3. So we know our horizontal one has to be 22.3. Because our 22.3 plus 14.7 is the same thing as 26.6 plus 10.4. So now vertically, we want to do the same thing. So our before, we've got a negative 6 plus a 22.3, and that's going to equal 6.8. So that gives us 16.3. On the left side, let's subtract the 6.8. And when we solve that, we get a y of positive 9.5. So what does that mean? Well, that means if we got a final answer of 9.5, that means we're going upwards, not downwards. Okay, so that's one thing you got to be careful, and you don't really know that until you actually do the math. So let's go back to this diagram again. It was drawn as though that blue one after would move downwards. But if we think about it, the initial blue one has way more momentum. It had a momentum of 35 almost. The red one only was 12. So, and it's going at a steeper angle. So when they collide, because it has way more momentum, it's going to likely just end up going almost straight through, and the red one will be the one that gets bounced off. Okay, so it does make sense that our blue ball one ends up going up above the horizontal instead of back down. So I think we're good calculation-wise. So now our final step, just like the previous example, we've got our final vectors. We just need to figure out what is that side, what is that angle. So once again, we can just use trig, Pythagorean theorem, and we'll find the angle as well. So we get 24.2 at 23 degrees. So just like our last question, remember, if we go back to the original question, it was asking what is the velocity, not momentum. So once again, to get our velocity, we need to divide by the mass. So 24.2, the mass was 2.31. So if we go 24.2 divided by 2.31, we get a final answer of 10.5 approximately. So that means we'll have 10.5 meters per second, and our angle is 23 degrees above, so we'd say 23 degrees north of east. And that'll be our final question. So let's go back and kind of see if that makes sense. So 10.5 going at 23. So if we go back to our original one, let me clear all of the writing here. So let's see, our original one was 1.2 kilograms. This one was 2.31, so the blue one was quite a bit larger. And our red one was going down at 10, the blue one was going at 15, so it was quite a bit faster. And then after the fact, our collision of the red one was 13.5, and our blue one didn't go downwards, it ended up going upwards. And we calculated 10.5. So if you think about that, the blue one was going faster, it hits the red, it shoots the red a little bit quicker, so it gave the red some speed, but lost some speed, so it drops down to 10.5, so that seems realistic. And if we look at the angles, right, we calculated that the blue one ended up moving upwards, and when we do the calculation, it's at 23 degrees, so it ends up being almost in line with the red. So this kind of goes back to we talked about when you have car accidents, you have a big, huge semi, lots of momentum, it's almost going to end up going pretty much straight through, and the red one just kind of gets pushed in its same path. So it's almost the same thing. The blue one, the momentum and the direction kind of is dominant, so it's going to plow straight through, and the red one gets sort of bounced off and in the same. So that's it for this question. There's a few homework book questions you can try, and we've got the online assignments as well.